Welcome everybody to one more iteration of our Montréal MLOpt seminar series. We have our distinguished guest speaker today, Lenka Zdeborova. I hope I said it right.
Perfect.
Dr. Zdeborova is an associate professor of physics and computer science and communication systems, all of that, at, if I'm not mistaken, at EPFL in Lausanne. And she leads the Laboratory of Statistical Physics of Computation. So one of the big things I promised to some of our attendees today is they'll get a glimpse on why physicists seem to be playing such an important role in fundamental machine learning research these days. And sometimes they're getting some of the best jobs. So
that sounds ambitious.
So we're very excited to have you. So welcome, and the floor is yours.
Thank you, Ioannis. So, well, thanks everybody coming. So yeah, I don't know. Ioannis set such an ambitious goal here today. I am less, I just want to discuss with you some insights that we got by fooling around with few toy models about gradient descent based algorithms in high dimensional and non-convex optimization. So it's a series of work that you see my mouse, right? Yeah, you do. That I done with a bunch of collaborators. So Giulio Biroli, who is in Paris, Chiara Camerota, who is in Rome, Florent Chakala, who is in EPFL here, Stefano Manelli-Saraho, who is a PhD student in our group, Eric van den Eyden, and Francesca, who is a currently PhD student in our group, and Pier Francesco Urbani, who kind of is a... So I decided kind of to skip the high level introduction because I think that you guys are discussing about optimization and gradient descent and deep learning for a while now. So just in a very kind of succinct form, what is my goal today is all kind of broader goal to analyze the whole trajectory of gradient-based algorithms in non-convex and high-dimensional problems at really low sample complexity. So, the kind of eventually we would like to understand why current state-of-the-art deep learning systems are working. Those certainly are non-convex and rather high-dimensional. Do they have low sample complexity or high sample complexity? Well, definitely they do have a limited sample complexity. We are not optimizing the population loss, we are optimizing the empirical loss. So I want to kind of stubbornly stick to that, even though that's a kind of more complicated setting than thinking about the population loss. So if I should put in 3 points, the kind of key 3 points that I want to keep in mind, if that I want from the systems that I study, I want to limit the number of samples, I want the system to be non-convex, and I want it to be high dimension. So that's kind of ambitious given how little we kind of know how to say theoretically about these systems. But it's needed because if we kind of think forward, at one point we will get some theory of deep learning, we will have to that theory will have to address those, because we know that local or even global minima with bad generalization error do exist. So the theory that is going to explain why gradient descent works in the state-of-the-art systems, it will have to kind of deal with that, and it will have to explain why the algorithms actually don't go to these and go to those where the whole system works nicely. So how do actually gradient-based algorithms manage to avoid the bad minima with limited number of samples is a big question. It's kind of no real satisfactory answer yet there, even though there are really many papers, many really interesting ones discussing things like no bad local minima, but I kind of cross that here because I really believe that's not a way to kind of go after the eventual answer. More interesting things such as implicit regularization or learning simple functions first, etc. So this is just kind of to put this into context. Now, I kind of set an ambitious goal, And I will not be answering it in the generality of kind of deep learning as this slide is maybe suggesting, because since it is so ambitious, I kind of have to pay some price to be able to do something non-trivial and still solid. And that price in this line of work is that I actually restrict to toy models of data, the analysis and the considerations. So unlike in most of, say, like learning theory that you have say followed in your graduate classes, where you try to keep the data and their properties and the properties of the function as generic as possible. You sometimes assume some kind of smoothness and regularity, but you really try to be as generic as possible. Here I really go like completely upside down. I just assume a generative model for the inputs, and I assume that I know from which function the outputs came. Of course, the algorithm that is learning is not knowing it, but for the purpose of the analysis, I do know it. So that's kind of, I go into those settings. That's the price I pay to be able to keep, and I repeat here, the sample complexity finite and the problem, truly non-trivially non-convex, and the dimensionality of the input high. And the two toy models that I will be talking about today, and we will be going through what we actually learned and what we know about the behavior of gradient flow and stochastic gradient descent and Langevin dynamics and all these gradient-based algorithms, will be the spike matrix tensor model that I define on the next slide, and then the phase retrieval teacher-student model with Gaussian IID inputs. That will be the second half of the talk. So I will define that properly when I get to it, for those who don't know. So the first model, so what is this? It's the optimization problem, where the loss is the following. So the loss on variables x here is a vector that lives on n-dimensional sphere, and n, I will be thinking of n going really large. So the loss function is a sum of two terms in this model. One is this square of difference between x transpose and a matrix y, and the other one is like similar, except that it's x tensor product p minus a tensor t. So this is just xi, xj up to x, or you can say xi1 up to xy, x product up to xip. Where this y and t are not arbitrary, those are actually created from some, you can say ground truth or signal vector x star that is also living on n-dimensional sphere, plus noise of zero mean and variance, and certain variance that is Gaussian. So every single component of this matrix and of this tensor is this outer product of the vector x star, plus for each component an independent Gaussian number with zero mean, and this is the scalar variance here of certain amplitude. And the goal here is, can we by minimizing this function, this loss function, can we find back the vector x star or something close to x star by gradient descent on this loss? So maybe okay, one realization is that why do I study such a model? So one realization is that model actually corresponds to spike matrix tensor model, kind of a mouthful of a name, actually corresponds to a model that is very well known and studied in statistical physics of disordered systems. I just need to write things a little bit differently. So here I kind of define the noises with explicit terms that depend on n, and that end up to be the strength of the noises, such that if I had exponential or infinite computational power, then information theoretically, my ability of solving this problem would change as I'm changing this noise from something, say 0.5 to say 10. And the same for this noise here. So that's kind of the information theoretically kind of relevant scalings here. And if you write them this way and you just rewrite the loss function, you forget all these terms that are actually constants and do not depend on the x, either because they just don't, or because since the vector x lives on a sphere, they just end up to be trivially some constant. You can rewrite this loss function into this form, which in physics we would call a Hamiltonian, and this ends up to be a Hamiltonian of a problem that is studied in the physics literature. It's called the mixed 2 plus p spherical spin glass model. It's kind of studied since 80s, 90s. So far, this is just rewriting. This doesn't tell us anything about how algorithms behave on this problem. One slide on why this problem. So not only because we know it in physics, but going back to my ingredients that I wanted. Well, it is high dimensional. The dimension here is the n. It will go to infinity. That's the limit in which I'm thinking about this problem. It's non-convex because of the tensor term. The matrix term, that would be simple, but the tensor term is making this very bumpy loss landscape.
And can I ask a question?
Sure.
So if we throw away the tensor term, we get something like principal component analysis.
Yeah, exactly. That's the third point in essence here. So if I saw both the spiked matrix and the spiked tensor, which means that I'm in the spiked matrix, I'm throwing away the tensor, and in the spiked tensor model, I'm throwing away the matrix. Okay. So both those, if I just have one of those terms, are relatively well studied. So of course the spiked matrix, it's even more so. That's exactly like Ioannis is saying. That's solving it would just be by principal component analysis. You just need to find the leading eigenvalue and corresponding eigenvector of the matrix. And the spiked tensor model is actually really difficult in the sense, algorithmically, in the sense that the best algorithms that we have for that model, they actually start working at the value of the signal to noise ratio that is completely, even in the scaling, away from the information theoretic value of the signal to noise ratio, where it would be possible, if we did not have algorithms constrained to run in polynomial time. And that's why combining the two makes it interesting, right? So the matrix is too simple alone, the tensor is too hard alone, but if you combine them in the way I do, then for the scaling of parameters that corresponds to the information theoretic thresholds, something interesting happens computationally. And that's why we combine them.
And a quick follow-up. So if I just look at the first term, this spiked matrix, it's still a non-convex problem, I think, right? It's a very easy case of a non-convex problem, I think.
Yeah, because of the symmetry. It's it's non-convex because you have overall symmetry, but that's this type of benign non-convexity that actually doesn't render things. So the SDP people call it this way. It doesn't render things algorithmically difficult.
Right. So, and related to that, you will always have one spike, a single spike X, right? Not more than one. And so if we look at if we focus on the second term, this tensor term, do we get local minima that are suboptimal? Clearly not global.
Yes. Okay. Yes, absolutely. Okay. That's I will be showing you that, right? And understanding why in this case we go around them. That's in a sense the interesting point where I want to get. And the fourth point, so okay, I skipped the second. That's that, this is an inference problem in the sense that I'm trying to recover the X star. My primary goal here is not really to solve the optimization problem. Right? So I like that because that's common point with the learning, right? We solve learning by optimization, but our goal is not to find the global minima. Our eventual goal is to find a good test error. So in that sense, having a problem where there is, we do optimization, but we want to be close to some ground truth, and that's not the same. It's related to the learning problem as opposed to just pure optimization. And the fourth point is that I can actually say something explicit about the dynamics. So that's why we picked this model, but that's of course is not clear at this point. So just, so this is a probabilistic inference problem, if you want, that I solve by optimization, but I just want to state here what are kind of the estimators that we would be typically discussing. So I will be discussing two of them. One, let me start with the second one, the maximum likelihood inference. That's, in physics, that will be computing the ground state. That's really taking the x for which this loss function is minimized. So that's what the gradient descent or flow aims at. Now, this is in a high dimension. This is not the optimal thing to do if you want to actually come closest to the signal x star. The optimal thing to do if you want to get the best error on the x star is actually to do base optimal inference, where you are computing marginals of the posterior probability distribution rather than maximizing the likelihood. And this is something that the Langevin algorithm is aiming at if you actually set the noise in the Langevin algorithm properly. And I will be looking at both. Keep in mind, this one is the more common one, but in this case suboptimal. And this, if I would be evaluating the marginals exactly, that's something that cannot be algorithmically beaten in terms of how close it will get to the x star. But then the question is, of course, if it is algorithmically doable. So now I have two slides with so I will be talking about gradient descent and Langevin algorithm. But I have two slides about different kind of analysis methods that for this type of model we understand well, and there is previous literature about them. And I will kind of go fast through them and do not explain the details, because that will not be my main point. I will be using these as a kind of point of reference. So this is about the what we know about the performance of algorithms called the approximate message passing, and about it reaching or not the information theoretically optimal performance, and about the analysis of the information theoretic optimal performance per se. So this is something that for this model we know how to do. This is, all boils down to a very simple expression that is here, the free entropy. And in the paper on the gradient descent in the appendices, we actually worked that out for this particular model. It just follows directly from some previous literature. There are like all the proofs that this is actually the right thing. So all that slide, boils down to this picture that explains to us what is optimally achievable and what is achievable with the approximate message passing algorithm. So what is this picture, right? So the axis here, remember we had the matrix, and that was the signal plus noise of variance delta 2. So this y-axis is proportional to the noise on the matrix. And the x-axis is inversely proportional, and the x matrix is proportional to the noise on the tensor. So the bigger noise on the tensor and bigger noise on the matrix, there's this corner here, we should not be able to recover anything about the signal. There is just too much noise, that's it. And in the opposite corner, when both these noises are very small, for instance, above the green line here, which is when the noise on the matrix is smaller than 1, well, that's the regime where even just only having the matrix, the principal component analysis, would give us a correlation with the x star. And now having the tensor, actually the approximate message passing algorithm gives us the information theoretically optimal performance on this problem. And this is something that in the limit of large size can be proven in this case. So that's kind of a regime where for some algorithm that is fine-tuned to this problem, we can solve it information theoretically optimally. In the red region, whatever algorithm we would have, even exponentially costly, we cannot obtain any correlation with the X star because the noise is just too large. That's kind of the information theoretically impossible regime. And the orange region is interesting because that's a region of parameters where information theoretically we could get a correlation with the X star, but the approximate message passing algorithm gives us strictly zero correlation. So that's why I call it hard here. And now the question will be kind of how do gradient descent and Langevin algorithm perform in this phase diagram, how good they are, right? Are they like, for instance, could they be better than the approximate message passing? So the approximate message passing actually is conjectured to be the best of the polynomial algorithms. So we don't really expect that they will be better, but are they matching it or are they worse? So that's kind of
question on hardness here. Is it known whether this orange region that's marked hard is efficiently solvable in the computational sense? Like it's not NP hard, for example.
So this problem in the worst case is NP hard. I mean, that's definitely the case. Now here, right here, I am defining some natural distribution over the instances of this problem. And I am sending the size of the instances very large. Mm-hmm. So when that is the case, you know, all these results are kind of high probability results. So when I say that it is easy, it means that it is easy with high probability over the instances, and the probability goes to 1 as n goes to infinity. So these kind of notions of NP hardness and computation complexity, they don't really, like, we don't know how to generalize them to this setting when we have a natural probability distribution and you want to be, you want something to be true with high probability. So in this sense, you know, nothing is known about kind of formally the hardness of this.
So it could very well contain very hard instances that put it into.
Oh, absolutely. I mean, the conjecture is that the conjecture is that no polynomial algorithm can actually solve the instances in this orange region.
Okay.
Now that's like, you know, that's very far from a theorem, because if ever there was proven, one would be proving on the way that P is not NP. So in some much weaker sense, something about it can be proven. That's kind of okay. But so we don't really expect that the gradient descent will be able to enter. But already, you know, can it match the approximate message passing or not? So that's what we go after. So let me just define what we usually mean with gradient descent. So we have this n-dimensional variable x, and its derivative is simply proportional to the gradient of the loss function. And then here I'm putting a term that is the weight decay, because the way I define the problem, I actually fixed the signal to lie on a sphere of radius, well, n or 1, depending how you think about it. And this, in a sense, this regularization, we will be setting it precisely so that the signal stays on the sphere. So that's just kind of our choice to restrict the optimization to the sphere. And then there is this noise term with zero mean and variance that is proportional to this constant temperature. Of course, if this constant is 0, then there is no noise, then there's just the gradient flow here. And if this constant is 1, then this leads to the Langevin algorithm. And the value 1 actually is the one that at exponentially large times would probably sample the posterior measure. So that would be the optimal algorithm to get after that base optimal estimator. But that's at exponentially large times, but our n is of course very large. So we will rather be interested what is actually happening at linear or at most log linear times. Like, are we actually reaching sampling the posterior or not quite? And so luckily for us, this fourth point that I said, that this model is solvable, that often happens kind of in my work, that there is some paper in physics, you see Physical Reviews letters, that's like the main physics journal, in '93, so a long time ago, maybe a lot of the audience was kind of born after that, where precisely kind of this gradient flow and Lanceval algorithm for a very close model has been solved. So we really can kind of take it and adapt it to our present model, and it's in a sense an exercise. It's straightforward. So this is the kind of equations that we end up with when we do that. So while they look a bit horrible on the first sight, but what are they? So I define here three quantities, C bar, and R. I define them with given n here, so finite size system. So this is a kind of correlation between where the gradient descent is at time t and t prime. This is where it is compared to the ground truth signal. And this is a kind of response function. How would the place where the gradient flow is change if we actually edit kind of a prior on position I at time t prime? And then we send n to infinity and end up, and then these same quantities without the n, those are the limits. And we end up with three equations, that are closed because, C depends on R and C bar, and the same for the other two. So this is a closed set of integral differential equations where there is no n anymore. These are low dimensional integral differential equations. So they look not friendly, right? But what we gained is that we started with a high dimensional problem and was very large, and we reduced the dynamics of the gradient flow into a set of three equations for three variables that have pretty natural interpretations, like the C bar is exactly the correlation with the signal. So that's something that you're directly interested to know, what's the correlation with the signal at the given time of the dynamics. And this, I just write two sets here because the fact whether I do the temperature here 1 or 0, that changes a little bit the equations, but not so much. So I kind of have two sets, one for the gradient flow, one for the Lanceval algorithm.
So is this all due to rotational symmetry here? The fact that
the
rotational to this three-dimensional problem, it's because you have I guess isotropic noise all everywhere, and then I think that's important.
So the rotational symmetry kind of plays some role in things, but it's not the key thing that makes it work. You can have other problems with rotational symmetry for which we have no clue how to write these type of equations.
Okay.
Yeah, it's kind of it's fair to say it's kind of a special case in the landscape of highly non-convex, highly rough landscape problems where something like that can be done. And we will then, when we switch to the phase retrieval, that will also be another case, but where it's actually a bit more complicated.
Okay.
So, there is, in the 90s, there is dynamic mean field theory in the physics that lets you write something like that. That lets you reduce the behavior of the algorithm to something that is just three closed low-dimensional equations. The way we derive them is non-rigorous from the mathematical point of view, but very close set of equations were actually proven rigorously in for instance, the one that was actually in that paper by mathematicians, probabilists. So it's pretty likely that one can also prove that these are correct, but it's something that we have not done yet. So if you're interested, you could kind of have a look at that. But so this is still on the level of a conjecture, but it's the type of conjectures that come from theoretical physics that are just true. It's just that we don't know how to put the epsilon and deltas everywhere at this point. So more interesting, what do they actually tell us about the behavior of the algorithms? So, so that's in this picture. As a function of time, how does the correlation with the signal depend on time? So just for comparison, I do here the same thing for the AMP, where the lighter the curve is, the smaller the noise was. So the smaller the noise, the easier it is to recover the signal, right? And so the higher the correlation should be. So indeed, for the AMP, the smaller the noise is, the higher the correlation is, and the sooner it becomes high. Whereas, so these curves are not crossing, right? Whereas for the Langevin algorithm, it's, eventually the lower the noise is, the higher the correlation gets. But the lower the noise is, the longer it takes to actually realize that it should start correlating with the signal. So that's kind of counterintuitive. There is something in the landscape, making it happen that you are lowering the noise, making things easier, and the Langevin algorithm just gets longer and longer to actually realize that there was a signal and that should actually be correlating with it. So when we actually collect these data, we realize that this time it takes to correlate is actually diverging at some value of this noise on the tensor. And when we collect these values, and I'm back at the phase diagram that I showed you before for the approximate message passing, but now I added to it a line above which the Langevin algorithm works and finds optimal correlation with the signal, and below which it doesn't. So notably, you see, the Langevin algorithm aims at the same thing as the approximate message passing. It aims at computing the marginals because it wants to, compute the optimal possible correlation with the signal. But there is this triangle where the Langevin algorithm is not managing it. It just stays at zero correlation, while the approximate message passing algorithm would actually manage. Or even you don't have to go to something that is fancy like the approximate message passing algorithm. I even told you that above the green line, if you actually forgot the tensor part and only did PCA on the matrix part, you would get correlation with the signal. And the Langevin algorithm that is running on the full loss is missing even that. It's actually not correlating with the signal at all. So you see, the fact that you actually add the tensor into the loss, it's actually making the landscape bumpy in a way that it completely makes the Langevin algorithm lost. And you may ask, okay, what about the gradient descent? Maybe it will be better. Well, no, it's even slightly worse. That's somehow expected because the gradient descent is going after the wrong estimator, right? It goes after the maximum likelihood estimator, which is actually suboptimal in this case. And yeah, there could be something magically happening that would actually make it work easier, but it doesn't. If I do the same analysis for the gradient flow, I get that it works above this line and fails below this line. So it's even slightly worse than the Langevin algorithm.
So just to clarify real quickly, it seems like what you're telling us is for a fixed delta 2, for a fixed level of noise for the spike matrix term, more noise for the other term can be better for those algorithms.
Yeah, so what am I do? So okay, that's it. Let me answer. So what I'm doing here, I'm generating the matrix and tensor with a given value delta 2 and delta p, and then I'm optimizing the loss for those. So I kind of know those values. I tell you those values. And kind of, if you're a Bayesian, right, and you know more about the system, then you use it in your algorithm. So you use those right values of the delta 2 and delta p. So that's the meaning of this phase diagram. But I mean, you were asking, right, because you are kind of seeing here that if you actually turned delta p to infinity, so to the wrong value, which is kind of turning off the tensor term, then the PCA would kind of kick back in, and you would start getting some correlation, and then you could be turning the delta p kind of back to its right value, and you would be killing this Langevin hard and gradient hard region. Yeah. So that's the case. So that's in a sense, kind of Yeah, that's the case in this model. The way I'm thinking about it is kind of a prototypical model of, you know, something interesting happening is in optimization. I just don't let you separate the tensor from the matrix. Like, I just let you look at the loss as it is, right? In a sense, if you really were just a optimizer that doesn't even know where the loss comes from, and I only gave you access to the gradients, you don't even know that it's actually sum of two terms.
Right, right.
So you won't be thinking about that, right?
And also, all of these are, you know, in the limit of n going to infinity, right?
Yes.
So
Correct.
for fixed n, this diagram doesn't necessarily tell me that by increasing delta p, I'm making the problem easier.
So not necessarily, but in these type of analysis, you know, the scaling is set in such a way that actually at n, that is, say, I maybe later I have some figures with the actual like finite n, that, you know, if n is something like 1,000, you basically see no difference from this asymptotic phase diagram. So you know, if n is of course 10, then things would be very different. But kind of this asymptotic behavior kicks very, very fast in these systems.
Okay.
So what's going on here, right? You know, I mean, kind of the naive explanation is, okay, there is some region where the landscape is trivial and some region where the landscape has local minima, and when there are local minima, the algorithms get stuck there, and when there are no local minima, the algorithms work as you kind of increase the signal to noise ratio. So the thing is that in this spiked matrix tensor model, we actually can describe in detail how many minima of a given kind and of a given correlation there are, correlation with the signal, that would be the n here, and at a given kind of value of the loss at the matrix and value of the loss, the part of the tensor. So this again, you know, is something that comes from previous works, is very similar to some works that have been done before. Again, I'm not going into the detail with this, just to say, you know, with the Katzreis approach in this model, we can actually compute how many minima there are at a given correlation with the signal and at given values of these energies, of these losses. And so we can actually kind of quantify that intuition. And you see here I had this purple line. And so I can actually compute where this purple line, where I truly only have one minimizer, where it actually is. And I will get this line here in the phase diagram. So it's yet a bit higher. And so notably, that leaves us this region in between where gradient flow actually happily works, but they are spurious local minima, provably in the system because of the Katzreis calculation. So you see that popular explanation is not quite correct, and we actually need to think better of what's happening here. And, you know, with all that we can actually say about the gradient flow in this model, we actually understand what's happening here when we look at the, you know, a different like upside down plot that I have already shown you. We actually see that as the loss, how the loss is going down, and we see that there is this kind of plateaus where it tends to get stuck and then abruptly escapes from it or not. So what kind of seems to matter is whether, you know, where it would get on these plateaus, whether these are well-defined minima or saddles. Not at any energy. If there were spurious minima at other energies than this plateau, then the gradient descent will just never see them with high probability. So what will actually matter is whether at that energy the, you know, stationary points are saddles or minima. And that's something that we actually can analyze, and, you know, leads to some equations within, again, like this type of theories, but to bring you and gives us explicit prediction for actually where the gradient flow and the gradient descent should fail. And this is kind of these are explicit predictions, but again, we don't have kind of the epsilon deltas on that. There are several assumptions that we use to get to these formulas. But if I plot these formulas, for instance, for the gradient flow, that would be the blue curve in my phase diagram. Yeah, that seems like that's the line that is describing what the gradient flow is doing, rather than this line above which there were really no spurious local minima. So it seems correct. So and the same is true that the green line was there actually since ever. That's actually the green line that comes from the simple formula. So what we are having here at the end is like a super simple formula how the two noises must be related so that the Langev algorithm works or the gradient flow works or not. So that's kind of there are not so many problems in the literature that are high dimensional non-convex where you can really get the constant for the signal to noise ratio where optimization starts working. So here, that's one of these cases. And in essence, what I just told you, I should correct this picture, right? I told you there is a precise level of energy, and it matters whether the stationary points at that level of energy are minima or saddles. And this is what divides whether the algorithms will be working or not. Because if those are saddles, you will go directly to the minima, and you will ignore the spurious local minima that are at lower energy, but the gradient descent never actually gets anywhere close to them. But if, of course, you do such calculation like the Katz-Rice, which is probabilistic, it's ignoring where the trajectory of the gradient descent actually goes, then you're seeing them. And if your kind of proof technique is based on their absence, then in this region you will never able to prove that gradient flow works while it does. So that's kind of what's a conclusion about this spike matrix tensor model. So just to summarize, that I showed you a closed form conjecture for the threshold above which the gradient-based algorithms work, and the existence of a region where bad local minima actually do exist while the gradient flow works. You could ask, this was a kind of inference tensor model. Is this applicable to neural networks, even simple ones? The second point, I told you that gradient flow was worse than the Langev algorithm, which itself is expected, but they were both considerably worse than the approximate message passing. So is there something kind of generic that you could do to actually make them work closer to the approximate message passing? I also told you that we don't really expect you can do better, but at least as well or closer. And I showed you that the gradient flow sometimes works even when there are spurious local minima. And what about stochastic gradient descent? Can we, analyze that one? So the second part is kind of trying to give some hint of an answer to these three questions on the other problem that I promised to talk about. But now I realize that I don't even, what's the time, Ioannis? I don't even have the watch.
Okay, so we have about 39 minutes left total in the meeting. You're welcome to take about half of that for sure, another 20 minutes at least, or 25 if you want, so we can leave a little bit of time for discussion. Does that work?
That works perfectly for me. I mean, it's a good time for questions. We can. I'm also happy to talk about what I already covered. Depends on you guys.
Okay. Since you're moving to since you will be moving to a different topic, maybe we can take a little bit of a pause to try to get back to the question that also came up in the chat. What were the salient properties of this spiked matrix spike tensor model that allow this kind of easy solution in this very high dimensional system? You get a low dimensional solution, right? So it's not necessarily, it seems like it's not necessarily the rotational symmetry, but there must be something else that one can potentially put their finger on and say that maybe this property is responsible for the easy solution that we have.
Yeah, so that's a really good question, and I wish I had a really good answer, but I'm a bit afraid that my answer is, yeah, this is like, even in the physics literature, this is like a bit of an outlier in kind of the type of models that we study for which the dynamics can be analyzed. So people often talk about mean field spin glasses, so some kind of a absence of a structure, that is not on a lattice, for instance, that it's somehow everybody is connected to everybody, so that's important. The fact that the additive noise was the fact that it was Gaussian doesn't matter so much, but that it was IID component from component, that's super important. If we broke this, then none of this would actually none of this, I mean, not none, but we would have much harder time writing something like that. Yeah, I guess that's the main ingredients, that the noise was IID in this way. I mean, you could imagine that the noise could correspond to, I don't know, something from the real world correlated in a tricky way, and that would break the way we derive these equations. And the kind of absence, the rotational invariance is kind of not enough, but the notion of like absence of any kind of structure that, there is nothing living, say, in 3D Euclidean space, that it's all connected to everything. That's the other ingredient.
Is there something about isotropy, like the fact that the noise is isotropic? I guess it would, if we didn't have isotropy, things would become more complicated, right?
Things would become more complicated, but that would not be impossible. That's, I think so.
Okay.
Yeah, we could definitely like think, I don't know, for instance, decide some of the dimensions and make the noise of one variance and in others of another variance, and this is type of things that could be included.
I see. So if you have
complicate things a bit, but not impossible.
If you have a limited number of noise levels in your model, then that kind of might dictate the rank of your system in the end. Kind of, right?
Yes, but the thing that would still be the noise, that would not be the signal. The signal would still, the signal here was also rank 1. It could easily, that's another important aspect actually. The rank could be not 1, but for instance 5, but it would have to, that's also something, a case to which one could generalize, but it would have to stay of order 1 as n goes to infinity. We could not make the rank, for instance, scale with n. That would also make the methods break at this point.
Okay. And there's another question by Igor in the chat.
Sorry, may I just jump in on this one, just as a continuation?
Sure.
So basically, I just come from a physics background, so for that reason, I think about things a bit differently than from a mathematical standpoint that you kind of described, from my point of view, at least. So basically, I used to think about always a mean field approach as a kind of a way to go from Langevin to Boltzmann or Vlasov equation, which is like a mean field, and the whole point was there to roughen the time scale in a sense. So for that reason, I absolutely agree that so the application that so I just saw the mean field there, and what you are saying, we are discussing with Ioannis right now that autocorrelation, like a noise, is important point when we are discussing physics. But at the same time, mean field approach is more like how I got used to thinking about it, is when you just go to rougher time scales. So you're not looking into the very small noise, but you are looking at the very small noise on a big scale, and then you can roughen it out. So I just wanted to ask whether you have whether any keywords hit something in your mathematical explanation. And also the question that I also wrote in the chat was, is it possible to provide the physical intuition, so for gradient descent, Langevin, and MP approaches? Because if there is a region where everything works, I just want to understand is it again related to this time scale Reyhane or something, where something works in one regime, then both work, and then something else works? Because I also don't see the coupling of losses in a sense. Like you have one term, you have another term.
So that's already a lot of questions. Let's take it one at a time.
Sorry about that. Yeah,
I've already forgotten what your first question was.
The losses are just added, right? And I'm not separating them. So in that sense,
right.
To your first question, so yeah, not quite. In the sense that, you know, in physics we usually start that we want to think, you know, of some like system that lives in 3D or in, you know, on a plane in 2D, and that's kind of where most of the difficulties, why kind of we have hard time describing dynamics very explicitly, is coming from. Here, when I define the problem, it's in infinite dimension, right? It's a, you know, in the physics terms, it's a mean field problem to start with. Yet describing the dynamics is still non-trivial because of the disorder, because of the noise. But the noise is kind of making it interesting as a optimization problem. So yeah, okay. I would have to talk with you more detail.
Okay, well, so interrupt. Well, I was asking so many questions because I would be happy to any comment in any related one. So I was just trying to throw as many keywords as possible. So yeah, so it's just in physics, I got used to coupling of. So you have usually one theory, and then you have some small lambda and a term which makes interaction of one with another, and I thought loss would be also having some lambda, and then lambda would make the regime go from one to another.
Because you try to solve things perturbatively, because you don't know how to go around the fact that you have strong correlations because your system lives in three-dimensional system. But all that is out in this kind of a system, right? That's a system where everybody is connected to everybody and everybody interacts with everybody in the same way. So it looks like, you know, a Curie-Weiss model in this sense, except that it's disordered because of the noise, and that makes things complicated. That's the complication. Cool. Not kind of the usual kind of, you know, correlations that are strong and we would kind of deal with them perturbatively.
Right. Okay. Well, it makes sense to me. Well, it's just also in QCD we have some coupling which also can be very strong, and yeah. So it's But I agree with you that
So in that sense, it's like the, you know, simplest like infinite dimension Gaussian model, but disordered, and that kind of makes it you know, non-trivial from the physics point of view.
Makes sense. So, and just because you mentioned the spin glass model, so right, it's a physics system. It's like not 3 dimensions, it's really high dimensional thing, and which describes kind of alignment of spins, right, at temperature transition. So I just wanted to ask whether maybe in the article or you can give some physical intuition for all the methods like gradient descent, Langevin, MP. So in this specific case, just maybe to grasp it a bit better, if possible, if you have any.
Sorry, in which specific case?
Yeah. So you're discussing this paper, right, from 1993, and it, as far as I understood, it is a spin glass model. So is it possible to kind of understand all these methods in relation to this model, which is in high dimensions, as far as I understand?
Oh yeah, absolutely, right. The Langevin dynamics is the like usual Langevin dynamics.
Okay.
And the gradient flow is just the one at temperature 0, where you just quench it to temperature 0.
Understood.
And the approximate message passing is not like a physical dynamics. That's in a sense like lifting the problem into a different space in kind of the better free energy optimization. So that's slightly different.
Understood. Thank you very much.
Thank you for your questions. Okay, so we took this little break. We do have a bit more time if you want to give us a quick summary on the phase retrieval problem. That's completely up to you.
Yeah, I mean, okay, let me maybe take 5-10 minutes to show you a bit about the phase retrieval problem, right? Because that's kind of going into the direction which we would like to go to do something like that looks more like a neural network, and this one looks more like a neural network, and we can do kind of, you know, we have some interesting other results there. So let me first, what's the phase retrieval? So, you know, in that comes from imaging and from kind of signal processing. But if you want to stick to neural networks, you can think about it as a, you know, single layer neural network teacher generating labels. So when I say single layer, I mean no hidden variables, really like just generalized linear regression. So the inputs would be X here, and that, you know, that would be your input data. And here, again, to simplify and be able to do some analysis, I just take the inputs to be IID Gaussian, like every component is IID Gaussian from every other. And then I have dimension D, and I have n samples. And then the teacher network has weights W star that, again, are Gaussians, and the labels are obtained as absolute value of the scalar product between the labels and between the weights and the inputs. So that's my way to produce pairs of labels and inputs on which then I want to do regression. And again, you know, here is just a slide. We know what to expect kind of from information theory and from the analysis of this approximate message passing. So how many samples do we need per dimension to actually be able to solve this problem? So information theoretically, we just need more samples than the dimension, just by counting number of equations. But algorithmically, the approximate message passing needs about 13% more samples to be able to reconstruct exactly the teacher weights, or to be able equivalently to be able to get zero test error. And now again, the same question: how compared to this does gradient descent work for phase retrieval? So which loss will I be minimizing here? I will actually minimize this, you know, it's a square loss, but what is inside is as if there was a quadratic, it's like no hidden units, but as if there was a quadratic activation in the kind of linear model. Because if I didn't put the square here and just did linear regression on X and Y, I would get zero, I would get as bad performance as random guessing for, you know, number of samples, that anytime number of samples would scale linearly with the dimension, I would get strictly nothing. So I kind of put or impose in the loss that there is this plus minus symmetry by putting there the quadratic activation. So that's the kind of loss that, you know, makes sense to want to solve this phase retrieval problem. And we can just, and again, we will be minimizing it with phase retrieval. So what is known about this kind of in theoretical computer science literature is, you know, not much about gradient descent and phase retrieval. I mean, there is a lot, but not much in the sense that the number of samples that you need for those results to actually hold is very big. So compared to, you know, alpha equal 1 or 1.13 of AMP, the best results on gradient descent of the same loss that I'm considering actually need polynomial of logarithm d alpha, so much more. And yeah, sorry, here there should not be a d here. That's just a constant, because here this is already the alpha. And then more recent work where one actually optimizes a little bit the loss with you know, for some properties to be able to prove what they were to prove. They can show that gradient descent would work with constant times the dimension samples, but for slightly different loss. But this constant is unspecified and potentially super large, so still big gap here. So can we kind of close that gap? So if you look at it numerically, you actually see for bigger and bigger systems that, you know, this is a fraction of success to actually get the exact reconstruction, that as the system is getting bigger, you know, first of all, somewhere at number of samples that is about, say, 5-6 times the dimension, it starts to work. But as the system is getting larger, it's shifting a little bit. So it could be a logarithmic shift or not. I mean, this is not so conclusive from this data. So, you know, numerics is getting, what is the constant here? Something like 7. So we don't really know. That's just like to give you an idea if you actually try it out for that loss. Now, can you do better? Can you kind of, even if it was 7, there is still a big gap between the approximate message passing and that gradient descent numerics, and more of it was shifting potentially in the wrong direction, right? So that's like even bigger gap. So how can we close the gap? And the kind of interesting conclusion of the paper that I want to mention briefly is that the over-parameterization does the job for you. So what can we show here? So now we take a different loss. We just over-parameterize a bit. We put M hidden units in the neural network. So one hidden layer, M hidden units. And we just need the number of hidden units to be, oh, here, I think I had D somewhere and here I have P. We just need it to be bigger than the dimension. So this should be D. D and P is equal. So the number of hidden units, we need it bigger than the dimension. So that's over-parameterized, but not like super a lot, right? We are not here comparing to the number of samples. The number of samples is kind of living on its own. So we just need it bigger than the dimension. So say mildly over-parameterized two-layer neural network. And for that neural network, what we could prove is actually that as long as alpha, so alpha was always the number of samples over dimension, is bigger than 2, then in a little bit in variables that are just the weights times its transpose, there is a unique global minimizer. If we have more hidden units than the dimension, and if alpha is bigger than 2. And if alpha is smaller than 2, so we have less than twice the dimension samples, then there are many spurious minimizers. Or we, in particular, we prove that the fact that the right one is not the correct one, that's probability 1. So, okay, that's like a weaker result, but I mean, morally, that means that there are actually many of them. And in this problem for the quadratic loss, we also actually have a convergence result of the gradient flow, that it actually goes to a minimizer. So if there is only one, well, it goes to that one. And so that altogether actually tells us that if we take this mildly over-parameterized network and just do gradient flow, nothing else fancy at all, we actually solve this problem to 0 test error starting from twice the number of samples than the dimension. So we push, this kind of results that are not so optimistic, we push it down to 2.
So the last theorem you showed us, it works on the assumption that this alpha equals 2?
This alpha is bigger than 2. Yeah, okay. Sorry, okay. Where is it? No, sorry, no. So this theorem is generic for any alpha. Sorry, but this theorem is just telling you that you go to a global minimizer, right? Okay. And the previous one tells you, well, below 2, you potentially had many global minimizers, so you cannot assure anything about the test error. But above alpha 2, you only have 1, and that's the one that has 0 test error. Okay. So putting the 2 together is showing you that above 2, you will go to 0 test error. And below 2, well, you will convert somewhere, but you don't know what's the test error. Okay. Well, it will be bad. I mean, these simulations here are actually showing us that it's nothing useful, okay? Again, here it's a bit hidden because we define, failure and success. Success is when we get closer to the signal up to, I don't know, 10 to the -5 or something like that. So it's not really like saying how bad is the test error when there is a failure, but it's bad. It's just close to random guessing. But what we got here is that, just by putting in hidden units, we actually get success for much lower sample complexity than what we could if we were not over-parameterizing. So that's kind of a nice result that I like about over-parameterization. That is, again, the fact that we are working directly with the empirical loss and we are not looking at the population loss, and this is, non-convex and high-dimensional problem, that kind of makes it pretty, there are not so many works that show something like that. I don't know of any. If you do, please let me know. And you could ask, could we do even better? So this, I don't know, could we close that gap? Is there a neural network architecture, or maybe, not just simple gradient flow, but some some other algorithm that would actually need less than 2D samples? So that I don't know. That's an interesting question. Okay.
Question. Sorry for the interruption. So so here you refer to gradient descent, but is the analysis technically for gradient flow, or is it for an actual discrete method?
Sorry, what did I click here? No, it's for the gradient flow.
Okay.
It's for the gradient flow.
Okay.
Yeah, here, we are not, okay, I would have to think a bit, like, it's not something that here seems crucial. We could probably like show that for some small step size, this is still okay. But that's, we haven't done that in the paper. But that's something that's not like something that I would expect to be a hurdle here.
Okay.
Because I mean, of course, when we run the numerics that like agrees very well with the two, we of course have some, I don't remember in the figure that I have what is the step size, but we of course have some small finite step size. And things seems to agree. And on the level of the proof, I wouldn't expect that to be a problem here. So then the last part was about, can we now do something for the stochastic gradient descent? And yeah, I don't know, maybe that's so there is this generic question, like, how is the stochasticity of the gradient descent actually crucial, and is that needed, and is that helping? So we just thought that this phase retrieval is like a wonderful playground to actually study that. But since we usually are looking at the gradient flow, that's kind of the case for which the dynamic mean field theory is written. What do we do for stochastic gradient descent, right? Because if the step size goes to 0, then stochastic gradient descent is just back gradient descent. So, well, if we analyze that, then we are just back analyzing gradient descent. Maybe if the noise is actually fat tail, this is not quite the case, but okay, that's not what we focus on here. So what we decided to do, we defined a variant of stochastic gradient descent that we call persistent stochastic gradient descent, that is stochastic, but that has a well-defined flow limit that is actually different from the gradient flow. So okay, that's that we thought that that's interesting, and that one we could analyze and see whether the stochasticity in that one actually does something. And here I'm defining it, and you see that it's not like so different from the stochastic gradient descent. So here that would be like generic kind of stochastic gradient descent with some variable here s that is telling that is 1 if that sample at that time step is considered, and that is 0 if that sample at that time step is not considered. And in stochastic gradient descent, this would simply be chosen 0 on 1 with certain probability that will be the batch size, or the fraction of the samples in the batch size. So that would be the usual stochastic gradient descent. And in the persistent stochastic gradient descent, we again choose this variable to be 0 or 1, but we kind of, if it is 0, we keep it 0 for a while, and if it is 1, we keep it 1 for a while. So we are not changing it every time step who is in the mini batch. We are the samples that are in the mini batch, we are keeping them for a while, and this time tau here, the persistence time, is the mean time for which we are keeping those samples in the mini batch. And that's all. So we have samples in the mini batch that are kept for a while, and when we kick them away, on average, we also put another sample in. So
like an exponential clock that
is, yeah, it's a Poisson, it's a Poisson process kind of. We decide for every sample when we put it in, and we decide like a Poisson variable how long it will be in, and that's the interval for which we let it in. Okay. And then we do that for all samples. We decide what is the interval there will be in. So there is the stochasticity, right? The samples are changing And if the persistence time is very small, they are changing very often. But for a fixed persistence time, this has a well-defined flow limit. We can then send the step size to 0, and there is no, you know, it's not that there is a problem with that with the stochastic gradient descent, but here it just does not go to the gradient flow. It's just a different algorithm. And then, okay, I will skip this. So we still do the same analysis, the dynamic mean field theory, but in this case, it's actually not leading to like so simple equations. They are kind of more, the spirit is the same, but the equations are more complicated. They kind of implicitly depend on two kernels that need to be self-consistently estimated. So it's kind of much harder to actually write and solve than the other ones. But okay, in principle, these equations are there. And this is just a plot showing that, you know, the simulations, which are the black lines with the error bars, actually do, you know, these are averaged over many instances. I don't remember how many exactly, but those actually follow the red curves, which is the result of the DMFT. So that's one thing that this plot is showing. But this plot is also showing another thing. So here I'm showing you what is the correlation. So this would be a performance measure. So better is, so higher is better. It's a kind of accuracy. Think of accuracy. It's magnetization is basically accuracy in this case. So higher is better. And we actually don't start at random. We actually worm start the gradient descent close to the teacher weights, just to put in kind of light the following phenomenon. So here we start at accuracy half. Here we start at accuracy 65%, and here 80%. And if we start at half, we actually get to something like 90% accuracy, and then we get stuck here. This is logarithmic scale on the time, so you know, if it's getting flat, we are really getting stuck. If it was linear, it would just be really long plateau. But then if we start at 65% accuracy, we actually go higher. We actually go to 1 accuracy. So this is bizarre in the sense, tells you how that low sample complexity, how complicatedly non-convex the landscape is, because you can get stuck something like 90% accuracy, but if you start at random lower than that, you actually get a better accuracy. So, you know, this could never happen in anything that is kind of evil somehow in a super weak sense convex. This is like very strange. It must be some kind of an octopus landscape where you can get stuck really close, but when starting far away brings you actually to the solution.
Question?
So that's somehow.
So your theory here, so this red curve is from your analysis, right?
Right.
And that your analysis actually tells you that it's what's happening on the left plot. I guess you're not getting stuck there for potentially exponentially long amount of time or something.
Yeah, not
right?
not exponentially. So yeah, that's a good point. I somehow went through it towards the beginning, but kind of fast. That this is the dynamical mean field theory is actually valid for time that is linear in the dimension. So that's really small time.
I see. So could it mean that if we run it for longer, it could eventually get unstuck?
So, okay, for the gradient descent, I don't know actually for the gradient descent, but definitely if we added a bit of a Langevin noise, then for sure it would get unstuck, right? For sure it would go kind of to the, if it can go to a better, in a sense, position, then it would go there, unless the noise is too big, in which case it would just be sampling the posterior at kind of a too high energy level. But adding a little bit of a noise would surely get it unstuck at exponential timescales. But that was also the case for the spike matrix tensor, right? That was also important there, that in a sense, all the results that I was saying were true for the timescales that are linear or at most log linear in the dimension. And of course, at timescales that are exponential, different things would be happening. But that's kind of why I stick to linear in the dimension. Well, because we are looking at high dimensional problems. So in physics, higher than linear, even quadratic in dimension is just not reasonable, because dimension is 10 to the 23. So in machine learning, dimension is not to the 10 to the 23, but say 1,000,000. So quadratic in million might still be okay, not completely useless, but exponential is definitely not fine, not okay, right?
Gotcha.
So this is just to show like how the different runs of the simulation actually look like. But then the red curve is in the limit of the dimension going to infinity. So we see that the finite size effects are actually really small. Like the average is already pretty close to the red curve. But sample from sample, there are fluctuations. And this was, I believe, 500 dimension. Francesca would know, but maybe she can write it in the chat. Something of that order. And then, another kind of realization that we had, now I make the sample complexity slightly higher and lower a bit the hot start. So I don't start so close to the solution. And that was a case where we kind of confidently persuaded ourselves that actually the persistent gradient descent worked better for some values of those parameters than even stochastic gradient descent could. So, and work better than the gradient descent. So not only overparameterization, but also stochasticity allows you to lower the sample complexity. So that's also something that, we kind of intuitively expect. And this phase retrieval example seems to be a really kind of neat setting where you can clearly kind of see that, and well-controlled setting. And this is the last figure. So that's just to say that for all these parameters that I mentioned, like the temperature and the Langevin and the batch size and this persistence time, that they all kind of seem to have optimal values. That kind of in the way we set these experiments, it was not like that the persistent time should be the biggest possible, the smallest possible, nor the batch size, nor the temperature. They all seem to be non-trivial parameters that actually, if you want the best performance, you kind of tune them in some way that we don't yet really understand what it should be, but they are all interesting parameters to explore. So just a take home. So from the first part, bad local minima do exist, but do not always stop the gradient-based algorithms from working. That's also actually the second part. And we are kind of trying to build a theory that faces it, that is not getting very far yet. I mean, so far we are at kind of level of these toy models, but it's still interesting what's happening there. And the dynamic mean field theory, that gives us low dimensional set of effective equations to describe the dynamics in these high dimensional problems. And that is applicable to these simple neural networks, and also to variant, not only gradient flow, but stochastic gradient flow. Pierre Francesco also has a recent paper where he has the momentum, so you can kind of do variants of the usual algorithms and look how this actually matters. And that's kind of what we are looking at currently, for instance. And I just end with kind of the list of the papers on which this was based. I should have changed the question marks here for the actual reference. It was some previous slide. Okay, now it's on the archive.
Okay, so we will make sure to share that also. I think it might have been in the announcement. Let's thank our speaker. Thank you, Lenka.